The major reason to study organic reactions is to understand them well enough to know how to apply them to make other compounds, an area we call organic synthesis. And electrophilic addition is an important tool in the synthesis of organic compounds. First, of course, we need to know the reaction facts. And secondly, we need to know how we can apply those reactions sequentially to make compounds that we want. So first, let me quickly review the electrophilic addition reaction facts, and then I'll cover a couple of examples of planning an organic synthesis using electrophilic addition. As I review these reactions, we need to keep two things in the front of our minds regarding organic synthesis. Some of these reactions have Regis selectivity or stereochemical aspects that are important to consider as we apply these reactions. I'll highlight these in the bright blue you see here as I summarize the reaction facts. Alcohols are made by treating an alkene with water and sulfuric acid. As you see here, the alcohol adds to the more substituted carbon, something we call Markovnikov Regis selectivity. There's a second way to accomplish this same reaction, using mercuric acetate, and in the second step, reducing with sodium borohydride. Again, we observe Markovnikov Regis selectivity. This reaction does not involve a carbocation intermediate, and so this is special. It lets you avoid carbocation rearrangements as you add water to an alkene. There's another way to add water to an alkene, and it gives the opposite Regis selectivity, something we call anti-Markovnikov Regis selectivity. And when we use this method, the hydrogen and the hydroxyl group added to the alkene carbons undergo syn addition. They're added from the same side. HBr adds to alkenes, putting a hydrogen and bromine on adjacent carbons, and this follows Markovnikov Regis selectivity, the hydrogen adding to the carbon that has the most hydrogens. We can add two bromine atoms to an alkene to make a 1,2-dibromide, something we call a vicinal dibromine. And the stereochemistry is special. Bromine is added with anti-addition, one bromine adding to one side of the double bond, and the other bromine adding to the other side of the double bond. And finally, we've learned a variation of this reaction. When water is also present, bromine adds to only one of the carbons, and a hydroxyl adds to the other. So we make a bromohydrin. Again, there's special Regis selectivity. Hydroxyl adds to the more substituted carbon, and this occurs with anti-addition. Hydroxyl and bromine adding to opposite sides of the alkene. Okay, so here we are. These are the reaction facts. Let's get a little experience applying those to synthesis. Suppose we need to make this secondary alcohol, starting with the bromide as shown here, a tertiary alkyl bromide. The compound we need to make is called the target, and the most effective approach to planning, called Retrosynthetic Analysis, involves planning the last step of the synthesis first, choosing what specific compound could be used to make the alcohol we want in one step. So let's do that. We have this alcohol, and we're asking ourselves, what could it come from? Well, we know that alcohols can be made from alkenes by adding water. So this alcohol could come from the alkene I've shown here. We'd be adding hydrogen to the more substituted carbon, and hydroxyl to the less substituted carbon. Alternatively, a second precursor is possible, this alkene, where we have the double bond at the end. Again, we can accomplish Regis selective addition of water, so the hydroxyl group can end up on the secondary carbon where we want. Of these two alkenes, we could make the top alkene from the alkyl bromide we need to start with. The bottom alkene wouldn't be made easily. So this is an easy choice. We'll choose to use the alkene that is shown at the top. So now we ask ourselves, what could this alkene come from? And in fact, we know we can make alkenes by elimination of hydrogen halide. The alkene we need could come from the alkyl bromide that we can start with. What we have left to do in our planning process is to write out the synthesis from beginning to end and fill in the reagents we need for each step. We'll start with the alkyl bromide to make the alkene, and to accomplish elimination we'll use a base, a rather small base. If we use a bulky base, we'll make the less substituted alkene, the so-called Hofmann product. We want the Zaysev product, so we'll use potassium hydroxide. To transform the alkene into our target alcohol, we need to add the hydroxyl group to the less substituted carbon. This is the anti-Markovnikov Regis selectivity. So for this transformation, we'll use hydroboration. Our synthesis can be accomplished in 2 sequential steps. We start with the alkyl bromide, eliminate HBr to make an alkene, and then add water to make the alcohol. Let's look at another one. Suppose we want to make this thioether as the target molecule, starting from an alkene, any alkene we choose. We'll use our retrosynthetic planning process. We need to decide what compound we can use to make the target in a single step. Well, we know that thioethers can be made by nucleophilic substitution. So as we plan this synthesis, we'll decide that this could come from the alkyl bromide that has bromine attached to the same carbon as the sulfur. Now we need to figure out how to make this alkyl bromide. Well, there are 2 alkenes that we could use, couldn't we, to add HBr to the alkene to make this alkyl bromide. This bromide could come from the alkene I've shown here, or the alkene I've shown below it. Of the 2 possibilities, we can rule out the top one because we cannot control the regioselectivity. When HBr adds to this top alkene, the bromine could add to either of the 2 alkene carbons, here or here. We can't control this because they have equal alkyl substitution. This would be a very poor precursor. On the other hand, when we use this other alkene, we know that we can add HBr with Markovnikov addition to put the hydrogen on the carbon that has the most hydrogens, and the bromine, where we need it, on the carbon that has an alkyl group attached. So our synthesis plan will start with this alkene and make an alkyl bromide. The alkyl bromide will give us the thioether we need by nucleophilic substitution. What's left is to write out the synthesis as I just described it, from front to back. We can treat the starting alkene with HBr to make the alkyl bromide. This gives the regioselectivity we need. And then we can make the thioether from that alkyl bromide by treating with a good nucleophile, this sodium thiolate. Now, as I've talked about planning these syntheses, I've mentioned the term retrosynthetic planning, also referred to as retrosynthetic analysis. It's a very efficient approach because you're always planning a step that can work. And as we use this retrosynthetic analysis approach, this special arrow replaces the words could come from. And each arrow points to the precursor that could be used in that step. So, in summary, for organic synthesis, step 1 is to memorize the reaction effects. And step 2 is memorize any special features of those reactions, such as regioselectivity or stereochemical preferences. Beyond that, use the retrosynthetic planning approach to plan the synthesis 1 step at a time, starting with the step that could be used to make the target compound.